Hey guys, welcome to the podcast on nonlinear regression and endpoint behavior. So really what we're trying to establish in this podcast is how you can tell if your data matches your best fit function. How do you choose between a linear best fit, an exponential best fit, a power best fit, etc. Oh, that's not good. Oh, there we go. So, we talked about this as part of our cautions about regression. Not all data is linear, right? So if I were to run a linear regression on these data, right, trying to put the best fit linear function, it's still terrible, right? Because these data are clearly not linear, right? So it's not impossible for me to actually do the linear regression. It's just not going to give me a result that is actually useful in predicting y given x or any of the other goals that we hope to accomplish when we do a regression. So when you do stat calc and go to do linreg, there are lots of other regressions that you can choose from, right? And here's what they mean. So quadreg, that means quadratic regression. LNreg is the logarithmic regression. Notice that it's not logreg, it's LNreg. Xpreg is exponential regression, power regression, logistic, and sinusoidal regression. So how do you decide which one of these is the one that fits your data the best? Well, you need to choose a function that matches the primary characteristics of a graph. So by primary characteristics, what do I mean? So, the data that I have here has positive x values and positive y values. So you should pick a function that has, positive x values and positive y values. That's a good start. Here, the best fit function should be increasing because as x gets bigger, y gets bigger. And then concavity. Here, the best fit function here should be concave up for this part of its domain, right? So the choices that really we have here, it could be an exponential function, it could be a power function. I could maybe come up with some other weirder functions. It could maybe be logistic. I could be looking at the bottom of a sine wave that could then go up, and do some crazy thing like that. But probably that's not what's going on. So we'd start with the basic choices of power and exponential. Oh, quadratic, I forgot. Okay, so endpoint behavior, this is all the same data set, I think, or maybe not the same, similar data sets. The functions might act the same in the range of the data, but they act differently on a wider domain. So here, right, this exponential fit, right, does pretty well inside the data, but what are the other properties of what's going to happen if I look outside the range of the data? Well, as x gets big, y gets really big, and it goes through some non-zero y-intercept, and x could be negative, and y goes towards 0 when x is negative. Now, it might be the case for the data that we have that it doesn't make any sense to think about negative x values, in which case it still can be exponential, but we want to make sure that all the data that we have matches what's possible for that function. Quadratic functions, it's still true that as x gets big, y is going to get big. It does have a minimum value, right? There's some lowest value that x can have. And as x gets smaller and goes negative, which is possible, y is going to get big again. That's very different than what happens over here with an exponential function. For power functions, as x gets large, y gets large. It goes through the origin. And generally, if we're using a power model, we don't think about the cases where x is negative because power functions don't all share the same behavior when x is less than 0, right? If I have a positive, when x is, or the exponent in the power function is 2 or 3 or 4, those functions, some of them go back up and some of them go back down. And even more importantly, when x is some random decimal like 1.5 or 2.289, it doesn't make sense to have a negative input because those fractional exponents correspond to roots, right? I can't take the square root of a negative number. Okay, so how do you figure out which one is right? It kind of depends partly on what the variables are, right? If these data, which this is the same two graphs, if this is time and this is the height above ground for our yo-yo, then probably I would not expect, like if I think about what's actually happening with the yo-yo, it's going to go up and back down and up and back down. And I probably want to pick a quadratic, which is like one time down and back up, or sinusoidal, many times up and down. Now this one, how long a snake is versus how much the snake weighs, right? This would make sense for V power, right? A snake that is no feet long doesn't weigh anything. Negative lengths of the snake don't make sense, and very long snakes weigh a lot. This is all consistent with the idea of a power function. You should also check to make sure that your scatter point doesn't indicate that something's screwy with your endpoint behavior. In this case here, right, the point that is on the end of the data is the furthest from the best fit line, and that's a really good indication that your endpoint behavior is incorrect for the function that you've tried to fit through the data. Here, the point on the end is no worse than any of the other functions, which means it's potentially a match for endpoint behavior. Notice that this is not the only way that you determine endpoint behavior. This is just part of the decision of endpoint behavior. You have to use what you know about the functions in order to determine whether the function is the best fit for your data. That's it.